I'm not able
Sujit
to
will
share.
join, no? Sujit will join, your student. Yeah,
Yeah,
Sujit has
he's
already
already.
joined.
Yes, sir. No, no, actually, I can't share the screen. It is sharing is
Yes, yes,
disabled.
I'm giving the option. Now you can share the screen.
Okay, right.
Sir. Now just try to share. Sir. Yeah.
Yeah, hope screen is visible to all, I guess.
Yes, yes, sir.
Yeah, right. Okay, okay. All right. So, yeah, so let's continue our discussion. So we have seen the neural network, a single neuron model, which is capable of learning the linear discriminant boundary between the two classes. Okay. So now, as we also seen that, okay, it is unable to learn any nonlinear boundary. So now we need to extend the same concept to learn the nonlinear boundary. That is where we go for the network of neurons. Okay, instead of having a single neuron, we'll have this network of neurons, which is commonly we call it as a neural network, or a typical form of a neural network, which we will be discussing now, is what's called the feed forward neural network, and in that specifically fully connected neural network. Okay, so in the fully connected neural network, or in kind of this feed forward neural network, so usually the architecture is something like that. It has several layers of neurons will be there. The first layer, we call it as an input layer, where only the inputs are given in that input layer. And we have a last layer, is called as the output layer. And in between, we have one or two hidden layers, or more number of hidden layers. And each layer has some fixed number of neurons that will be there. So remember here that when I say the neuron, this is simply the same neuron which I discussed earlier, the same single neuron. Now instead of having the single neuron, we have the multiple neurons. Okay, so just to differentiate between the those neurons, so if you see that the input layer, number of neurons in the input layer is basically, it depends upon the number of dimensions or the features in your input. Okay, and typically the input neurons in the input layer, they are called as the linear neurons. That is simply whatever the input you are giving to that neuron, same input is given as an output from that. Okay, it is simple, the linear neuron. It is simply the input layer we are talking about. Okay, and then the hidden layers, the neurons in the hidden layer. So it is around the neurons are, they're called as this, either the sigmoidal neuron, or they're also called as the rectified linear unit, depending upon the what kind of an activation function we'll be using in that hidden neuron. Either the sigmoidal activation function, like what we already seen, that the tan hyperbolic or the logistic activation function that is commonly used, or in the recent days, they're also using the rectified linear unit as an activation function. Okay, so but output neuron, typically it having the softmax activation function. Basically, the output will contain, basically, the given the input, what is the probability that that particular class has come. So that's a probability of class is a output. That's why in order to get that, the activation function used in the output layer is the softmax activation function. We'll see that quickly now. Okay, so sigmoidal activation function, we already discussed that. That's the same thing we used actually. Otherwise, the rectified linear activation function, basically what the difference from the logistic activation from the sigmoidal activation function in the rectified activation function is that, so whenever my activation value A, if it is negative, okay, it takes the value 0, and whatever the positive value of A will be there, that will be considered. Okay, basically it truncates all the negative value of the activation. Okay, so in case of the sigmoidal activation function, whether it is a activation value is negative or positive, the output will be bounded in the range of 0 to 1 or the -1 to +1. But in the rectified linear activation function, so whenever the activation value is 0, it less than 0, it's a negative, it's considered as negative, and only it considers only the positive value of the activation. Okay, so this has arrived because during the deep neural network, when you have the large number of layers of such neurons are there, this sigmoidal activation function tends to their output tends to close to 0, and then that leads to what is called as the gradient becomes 0. So in order to that affects the training of the neuron, okay, of the network. So in order to overcome that, this rectified linear unit or the rectified linear activation functions are used, because it's only considered only the positive activation values. So, and also computation is simpler as a result. So this has become more popular in the recent days in the context of the deep neural network. So this rectified linear function is used. Otherwise, the softmax activation function is widely used. Okay. So now the question comes is that, okay, how many number of neurons will be there in each of the layers? Okay. So the number of neurons in the input layer, it depends upon the what is the dimension of your data vector. Suppose if you consider that the speech, the oval recognition, where we are representing a speech vector with the two feature vectors x1 and x2, that is your formant frequency 1 and formant frequency 2 time. So in this particular case, the dimension of your vector is 2. So the number of neurons at that time will be only the 2. Input neurons will be 2, because only the 2 input features are. So the number of neurons in the input side is governed by the number of features in your input side. And the number of neurons in the output layer depends upon the number of classes that is used in the classification. Suppose if you are building a model to classify all the 5 ovals classification, then your output will be having the 5 outputs. Suppose if you are classifying only the 2 classes, then your output will have the single neuron. Output layer will have the single neuron if you are having only the 2 classes. Okay, so that is the. But the number of layers in the hidden layer and the number of neurons in the hidden layer, that is experimentally it is decided. Okay, so there is no fixed rule that okay, this is required only this many number of hidden layers required, this many number of neurons in the hidden layer is there. That is only the some thumb rules are there, how many should be there, but in general it is experimentally it is decided. Okay, so now here the connection. So here this fully connected neural network, it's also called as the feed forward neural network, because if you have seen this typical network architecture here the connection is feeding forward to the next layers. That is, the output of one layer is given as an input to the neurons in the next layer, right? So that's the reason why it is called as the feed forward neural network. That is, here the inputs are the information is propagated in a forward direction. That's why it's called as the feed forward neural. And why it is called a fully connected neural network? Because every neuron in a hidden layer, say for example in this, every neuron in hidden layer is connected by the every neuron in the previous layer, right? Similarly, every neuron in a output layer is having the connection with the every neuron in the previous layer. That's the reason why it's called as a fully connected neural network. Are you with me with this? And most importantly, every connection from one neuron in a previous layer to the neuron in the next layer, it is having a weight is associated with that. A weight value is associated with that. Okay, so put together, all the weights put together forms a matrix of the weights. Okay, so that is the weight parameter. They indicates the parameter of the discriminant function what we are trying to learn. So here the weight parameters are interconnected here. A complex nonlinear discriminant function can be learned. Okay, are you with me with this? It is trying to approximate a complex nonlinear discriminant function or the nonlinear decision surface. Okay, so that is the strength of this network of the neurons what we are trying to do. And what is the implication of having the weights of each of the connections here. Is it clear here? Is the structure of the feed forward neural network is clear for everyone?
Yes, sir.
Right? Okay. Now, the question comes now is that, so how do we learn these weights? Okay, now if you see here, every connection has weights now. Now earlier we have only single neuron and the input to the connection to that having only the weights associated with that. Now here, for every connection has a weights here. Now the number of weights have become increased. Now the question arises, how do you learn this particular weight? Okay, so the learning algorithm, what it follows is what is called as the back propagation learning algorithm, and it is again depending upon, it is based on the concept of the gradient descent method itself. Basically, we are trying to minimize the error, and in the error surface, we are trying to find the gradient with respect to the weight values, and then we are trying to minimize that. So here our objective function is to minimize the error between your output of the network you are giving and the corresponding to the desired output. We are trying to minimize this objective function. So in order to do this error propagation algorithm, what it does is that it has two operations. One is what is the forward computation, and another is the backward computation. In the forward computation, we compute the activation values. That means, so for every neuron, we compute the output of the neuron as a weighted sum of the inputs to that. Okay, and then we apply the activation function to that and then get the output of the neuron. And this output of the neuron will be fed as an input to the neurons in the next layer. And there also we find the output of the neuron. Like that, we do it till the last output layer. Okay, so and then we apply the activation function to get the what is the probability of that particular class for the given input, so that the output we compute that in the forward computation. Okay, and in the backward computation, we'll be compute the error, and then in the backward direction we start update the weights with respect to the in each of the layers. Okay, that is what we do in the backward computation. Now, if you look into the forward computation, what exactly we are doing to see that. So earlier, with respect to the single neuron, we just computed the activation value and we applied the activation function and got the output of it. So now here we have the layers having the multiple neurons will be there. So for example, for the sake of understanding, I'll consider only the three layers: input layer, one hidden layer, and one output layer. Okay. So let us having the D number of inputs are there in the input layer. Okay. That means the D number of features, I can say that. And there are J number of neurons in my hidden layer. And then there are K number of neurons in my output layer. That means that I'm having the K classes that I'm having. Okay. So x1 to xd are my D inputs, and then corresponding s1, s2, s3, the suffix, the superscript O indicating that it's the output of the output layer. Okay, there are k such outputs will be there. Okay, now, so for any input vector, we are having the D input values are there. That is the input to the input layer, and whatever the things these inputs are there, they are all fed as an input to the neurons in the hidden layer, and each hidden layer produces an output, that is the activation value A1, A2, and superscript H indicating that it's the output of the hidden layer. Okay, all right, fine. And this activation function, this activation values, vector of activation values will pass down, the activation function will be applied onto that to get the output of this hidden layer for this given input. Okay, and this output of this hidden layer will be given as an input to this neurons in the each neurons in the output layer, and it produces the activation values at the output layer A1, A2, E3 is superscript O indicating that it's the activation values at the output layer, and then the activation function is applied onto that to get the output, actual output from the neuron, from the network. Okay, so this is the propagation of the inputs in producing the output in the forward direction. Okay, now there is a connection from every neuron in the hidden layer has a connection from every neuron from the output layer, right? Suppose there are D inputs are there, then the first hidden neuron will have the D connections plus one connection from the bias. Like that, every neuron in the hidden layer has that D plus one number of connections will be there. And associated with every connection, there is a weights will be associated with it. Similarly, from the hidden layer to the output layer, we have the connections. Okay, all right. So is it clear with respect to that? Now, if you look into the only the connection from the input layer to the hidden layer, okay, what we have the output the weights. So here the weights I am representing as a WH. Okay, W is the matrix I am considering here. So now if you consider the first row of this matrix, this is basically, it is the from the weights from the basically from the jth, from the ith input neuron to the jth neuron in the hidden layer. Every Wij indicating that. So this first row is indicating the weights from your bias, this X naught, what you're having there here, to all the neurons it's indicating. In the second row, indicating the weights from the first input neuron to the all the neurons in the hidden layer. Okay, that's why the J such weights are like that. So if you look into this entire this matrix, it will be having how many such weight matrix it will be there? It will having the D plus 1 into cross J. That is the J is the number of neurons in the hidden layer. So that is the size of the weight matrix in the input in the hidden layer. Similarly, the output side also, for every WJK indicating the weight from the Jth hidden neuron to the kth neuron in the hidden layer. Okay, so that's why the first row indicating all the K weight connection from the zeroth node, that is the bias side, and in the second row indicating the weights from the first neuron to all other neurons in the output layer. So total number of weights in this weight matrix will be J plus 1 cross K number of weight matrix that will be there. Are you with me on that? Is this convention, is this clear for all of you? Okay. All right.
Yes, sir.
Okay. Right. So now, if you look into the hidden layer, output of the hidden layer, if you consider that, so the activation value what you're getting is the A vector. So this A vector is obtained as a weighted sum of the each of the inputs. Okay. So that is I'm representing in the matrix representation or the vector representation the dot product between the X, which is the input vector, with the my weight matrix. Basically, it is nothing but it is the matrix multiplication between my input vector to the each of the weight vectors in that. So basically, it is nothing but this entire row indicating the weighted sum of the input to the that particular neuron. Okay, so totally it is something like each of them are the weighted sum of them. So how many such rows it will be there? It's equal to the number of neurons for each of the neurons, because each A1, A2, A3 up to AJ, they are the output of this activation values of each of the output. Okay, and on that we apply the activation function. So after activation function is applied to each of the output of the neurons to get the activation, the output of the neuron. Okay, this complete output of the hidden neuron, the activation function is either the logistic activation function or the tan sigmoidal activation function, or it may be a ReLU, rectified linear activation. Okay, so that is what we will be doing. That is in the input to the hidden layers. Now the output layer side, the output of the activation values at the output layer, there is the A1O, A2O up to 8KO. So this is nothing but this is the weighted sum of the output of the hidden layer acts as a input to this the output layer, and the weights from the hidden to the output layer. So that is again it is the weighted sum from between them, and that is where the number of such weighted sums will be equal to the number of neurons in the output layer, and that is what is the activation values associated with each of the output neurons. And these activation values are applied through the activation function will be applied to that. Here the activation function we are applying is what is called as the softmax activation function. Basically, it is the exponential operation on the each of the kth output activation value divided by the sum of the exponential of each of the activation values. Basically, it makes the value of the SK, that is the output of the output neuron, in the range of 0 to 1. Basically, it's indicating the probability of the output. Okay, basically probability of the output, that's nothing but each neuron corresponding to one class. So the probability of the class given the input. So that is what we need to do that. Okay, are you with me with this? and the sum of each of these things will be equal to 1 because it's a probability we are computing. Is it clear for you, all of you? Is the things clear what we compute in the forward direction?
Yes, sir. But sir, one question: what is the purpose of this hidden layer then? I mean,
No,
we will
that's
creating
exactly the thing.
two.
Hidden layer is going to give you the kind of a non-linearity. It's going to learn from the data. Okay. So that
So
means that
here
your
we.
discriminant function is non-linear.
Yes,
See,
sir.
the thing is, what happens is that each neuron is learning what? Each neuron is learning one linear boundary, right?
Yes, sir.
Okay.
Yes, sir.
So now
For
each one
for
is
each.
learning a linear boundary. Now what happens to this output of the neuron? It will be a sum of the outputs from each of the things. What happens there? You will be stitching the multiple linear boundaries. Are you with me with this?
Okay, sir. So for
When you stitch the
the.
multiple linear boundary, maybe one is something like this, another something like this, another something like this, another something like this, another something like this. So then what happens all together, if you see, it is giving us some sort of a non-linear surface it is trying to learn. Are you with me on this?
Yes, sir. Got it.
Yeah, that is the idea of that's a because now if you increase the number of hidden layers, it tries to learn the more and more complex non-linear boundaries. Right? That is what it's trying to approximate. That's the purpose of it. Hope this is answered for you, right?
Thank you, sir.
Okay, all right, good. Okay, so now this is what in the forward computation happens. Okay, now in the backward computation, basically what we do is that, so once we get the output of the network, we compute the error. Okay, how much the produced output is close to the desired output, and then we propagated it backward. Error will be propagated back. Okay, there is no connection, backward connection here, but error will be propagated backward. In the process of error propagated, it will update the or modify the weights in the successive layers. First, it updates the weights in the with respect to the error, it updates the weights in the hidden layer, hidden to the output layer, and then with respect to the error, it modifies the outputs in the weights in the input to the hidden layer. Like that, it goes all the way to the input side. So that's a error is back propagated in the process. It updates the weights. Okay, this updating of the weights will happen the same way as the gradient descent technique, finding the gradient and then taking the this weights associated. Okay, so here, so basically, when the error is being computed, so here, since we are computing the probability of the class as an output, so and since the that is the it's called as a probability distribution now. Okay, the output desired output basically we represent it as a one hot notation. That is, suppose the example belongs to the class 1, okay, then this will be 1, rest of the things will be the 0. Okay, so that is indicating that it's a what is that? So that is a discrete probability. It's actually the mass function we call it as actually 1 for that class, and then when the output when it is being predicted from the neuron, that is the S output, we'll see that. So the output will be is in the form of the probability. That means if your training example xn, it belongs to the class 1, then the desired output is 1 for that particular class label and 0 for the rest of the cases. Now, if it is actually belongs to that, then what the probability should be there is that this probability should be high, this value should be high, and all the values will be low, very close to 0, because sum of all these probabilities should be equal to 1, right? Are you with me on that? That is what is the output we are getting. Okay, so now the error function which you are computing, the error function should be computed between the two probability distributions. We can't simply subtract and then squared error can be computed with respect to that. We need to have a loss function which compares the two probability distribution. One such loss function which we use is what is called as the cross entropy loss function. And I'm not going to discuss more about that. Please go and refer what do you mean by the cross entropy thing. Okay, basically it is used for comparing the two probability distribution. What are the two probability distribution? This actual output as a probability distribution and the predicted output as the predicted distribution. Their comparison, it will do that. If they're similar to each other, then that loss will be small. And if they're dissimilar, then the loss will be high. So again, we will be correcting the error with respect to that, and we'll be using the error correction method. So basically, for every input, we compute the instantaneous error in terms of the cross entropy here, because error for any training example, it will be computed as the examples with respect to this. It is the sum of the error with respect to each of the outputs we'll be seeing there. K is the number of output neurons. It is a total. That's a sum which we'll be doing there. And this is what is the term which is called the cross entropy. Between it is the information content with respect to the predicted distribution, and this is the actual distribution for the k term. Okay, and here since y and k is 1 for that particular class and rest of the classes is 0, and this entire loss function looks like just a minus negative of the log of the output of that k neuron. Okay, so that is with respect to that. That's a loss. Okay, this we will be minimizing it with respect to the parameters of the network. Now the parameter of the network is a huge matrix of the weights. It will be updated. Okay, and that basically tries to minimize the cross entropy loss. Okay, so that is what we do it with respect to the gradient descent method. Okay, so I'm directly getting to the gradient descent method with the steps what it follows. It follows the same step as what we have done in the previous the single neuron case. There's no difference with respect to that, but here the number of updates will be equal to the number of weights what we are having here. That's the more number of such updates going to be there. Okay, so the procedure goes to things like this. My training data, what is given is that for there n training examples will be given, each one associated to some classes. Okay, with one hot notation, it will be represented with respect to the classes. Now I initialize my weight matrix associated with the hidden layer and weight matrix associated with the output layer with some random values, and then I'll randomly choose a training example Excel, and I do the forward computation and compute the outputs at each of the layers and propagate it to the further, and then finally I compute the output of each of the output layer, and then I'll compute the instantaneous error in the backward computation, and then once I compute the error, so then I'll update the weights from in the backward direction. First I'll update the weights from all the neurons in the hidden layer to all the connections from the hidden layer to the output layer. So basically for every jth hidden layer to the neurons in the jth neuron in the hidden layer to the kth neurons in the hidden layer. Okay, so that I'll taking the negative of the gradient, I'll be computing that, going to give me the change of the weight vector that I will be adding to the original value to update the weights. Okay, and then after that for the same output, I'll come from the input to the hidden layer, I'll compute the gradient with the error, same error with respect to the weights in the input to the hidden layer, and then I'll update the weights. Okay, and then I'll repeat these steps from 2 to 4 for all the training examples. That is okay, so that is the one epoch. Then after that I'll compute the average error, and then I'll repeat the same process with respect to from the step 2 to 6 again for all the training examples. Each successive epoch, I'll check my average error with respect to the current epoch with respect to the previous epoch. If they falls under the convergence criteria, that means that difference of the previous two errors is very small, then I'll stop the error, stop the training. Okay, so this is what the process of the gradient descent technique. In the process, so all the weights will be updated. Okay, is the things are clear for you? Is it fine?
I have a question in the chat box, sir.
Yes. Yeah.
Yeah. My question is that does that mean from the expression that you give for cross entropy, it seems like it's a negative value. So Does it mean that the cross entropy is always negative? If it is positive, what was that indicating?
No. So the negative in the sense is that because this is information, negative of the information content being considered. See, if you look into the entropy has the two things, right? So information content is always represented as the negative of the log of that event. Okay, that's the information content. That's meaning itself is that.
Same as the
Yes.
entropy in thermodynamics.
What is it?
It is same as the entropy in thermodynamics.
Exactly. The concept is the same, but it is application in all the fields. The same entropy.
Okay.
That's what is the information. That's actually the amount of uncertainty present in the data. It is actually
Okay.
it is a negative of the information. That's what is.
Yes. Yes, sir. Got it. Got it.
Same thing. That's a reason. Okay. All right. So hope the question is answered. Right?
Yes, sir. Yes. Yes.
All right. Fine. So now this is where you can see the beauty that why that hidden layers are there, neurons in hidden layer are capable of this. That's what I'm showing that with respect to a illustration that when it is learned using this gradient descent technique. So now I'll take the same examples, this one. So we've seen that the single neuron model has failed to classify this or learn this nonlinear boundary between the class. Okay, so it may be a circle or anything that discriminates them that's required. So just to illustrate that for this same input layer, so this is a two-dimensional data. That's why the input layer having only the two neurons I'm having there. I'll just taken one hidden layer with the three neurons. Okay, and there is a single output neuron because I'm having only the two classes, class 1 or 0 in that. That's why the single neuron there. So now what is I claiming is that so each one is learning a different linear function boundary with a different slope. Okay, and if I stitch them by combining these things, I should get a nonlinear. That is exactly the things happens when you see the output. If you look into this boundary, so one of the neuron is learning this is the boundary, and this is the linear boundary, and this is the linear. Okay, and when they are combined together, this weighted sum, when I do that, it gives some sort of a some sort of a stitched triangle you are seeing here. That is a nonlinear thing. Are you with me with this? Is the things are clear? Now, if I increase the number of neurons in the hidden layer, that triangle becomes more and more become closer to circular because it's a kind of a piecewise linear thing. They are combining that. More the number of neurons in the hidden layer, that becomes more and more finer outputs. Is that fine? Are you with me with this? Did you understand what is happening here?
Yes, sir.
Okay, so that's exactly the things happen. Now, even for this case here also, it tries to learn this nonlinear boundary between the two classes for the same three hidden layers. Okay, just to give more impact associated to that, if you consider this thing, so here the output, the design boundary should be something like this, the kind of a sine wave or something like that, it should come there. So that's where we used here the two input neurons and then 8 sigmoidal neurons I considered. Only these are two class cases. There's a one input neuron we are considered here. So the whatever the boundary you are seeing here, you can clearly see here is the piecewise linear you are finding. Right? There's a boundary that's clearly discriminating. Okay, single neuron would have been failed to train that because it would have been considered only the linear boundary to separate. So that is a okay. Similarly, such a complex things here. So here, this is where the number of increasing the number of hidden layer going to here. Two hidden layers I consider. One hidden layer as having the first having the 20 neurons, and then next having the 10 sigmoidal neuron. So it is capable of learning such a spiral kind of a boundary. Okay, that discriminates such a complex boundary. All right. So that is the strength of that having the more number of neurons. This is exactly things happens in the deep neural network. When we say the deep neural network, the number of layers are very large. Okay, it tries to approximate very complex decision surface, which you can't imagine that. So that's exactly the reason why the deep networks are capable of performing very well in the current day scenario. All right. So just to summarize what has talked about the neural network. So here The complexity of the model depends upon the dimension of your input patterns, number of classes you have, and the shapes of the decision surface. And in order to bind these shapes of the decision surface, we go for the number of neurons and the number of layers in an experimental fashion. Okay, so since one thing you should keep in mind here, now the number of weights that needs to be updated or the parameter that needs to be trained are very large. Okay, with respect to that, the number of training examples required to model them also should be very high. Okay, so that's the reason, unless you have the very large dimension, large data, so you can't robustly estimate the parameter of the neural network. Okay, so the that's exactly the reason why the deep neural networks came into a very big way when the huge number of data is available for us to train the model, so that it runs all the complex features, complex the boundaries between the classes. Okay, so the gradient descent technique, it has the problem of local minima problem, and also the conventionally the gradient descent technique has a slow convergence problem. And in the recent days, there are a lot of new inventions that happened in the optimization theory now to make the gradient descent technique much faster. Okay, all those Adam optimizers and all the things you might have heard about that. So they are all of the advances in the optimization technique made this gradient descent technique to converge faster. That's the reason why the neural network has become more popular nowadays. So usually nowadays in the literature, so if the feed-forward neural network, which one or two layers they are there, they're called as a shallow networks, and the anything that is more than 3 hidden layers, they are termed as a deep. Okay, so this is what the neural network that I'm covering. I just wanted to give the details, and then with this I'll stop at this point. And any questions, I'm ready to answer that, and then with that we'll move towards the kind of how to build a neural network in the Python as well as in the TensorFlow framework. That's what Sujit explained about. Okay, so is the things are clear so far theoretically?
Yes, I have some questions on this.
Yes, yeah, please.
With regard to the activation function, is there any particular factor to consider in the when selecting the activation function for a particular task or not?
What is it? Pardon? What did you say?
Is there any
Function?
particular factor? What I'm saying is that is there any factor to be considered when selecting an activation functions?
Yeah.
Like when you wanted to do a particular task, you go for softmax or ReLU. Is there any some factors to be considered before you
if
choose
you
any
are
of
dealing
this?
with a shallow network, softmax is sufficient. It's a good enough. Okay, that's good. All right. But if you are going for a very deep network, okay, in order to speed up and also in order to avoid certain problems, this because when the number of layers is very deep, the problem with this softmax activation function is that the gradient which is obtained on the function of the thing, so that tends to 0. When the gradient becomes 0, your weight updation will not go to happen. All right. So that is the problem with respect to that. That will be avoided when the ReLU is being used. So typical things what we say is if you are using the shallow network, it is preferable to use the softmax activation function. And if you are going for a deep network, it's always better to use the ReLU. Okay. Remember, this ReLU is useful. This is applicable only with respect to the feed-forward neural network I am talking about. That's a fully connected neural network. Okay. Another version of the fully connected feed-forward neural network is the CNN. In the CNN, ReLU is by default the ReLU is being used. Okay. And there is another kind of a neural network that is called the feed-forward and feedback together. That is what is your recurrent neural network or LSTM. In such cases, if you really pay attention there it is a tan hyperbolic activation function is used. There the ReLU is not the right. Okay, these are the things. Hope it answered your questions or clarified your doubts. Yes, is it clear?
Okay, Bala.
Yeah, yes, sir, but I have some differences in the ReLU. What's the differences between the Leaky ReLU and the normal ReLU and the parametric ReLU? So are they the same? So there are some differences.
Okay,
If
they
there is,
all
please
are
let me get it.
having they all are having the same outcome they have. So, but in some cases, the leaky ReLU and other things, basically, see if you know that in the ReLU, all the negative activation values are truncated to 0, right? If you look into the ReLU, yeah. So here all the negative things will be truncated to 0. Okay. So sometimes, in some cases, some data, this taking this negative, all the negative activation functions taking to 0 will have some issue. Okay. So instead of making 0, 0 is always a bad whenever there's a multiplication involved or whenever such computation is involved. So instead of taking that as a small 0.1 or something, it will be considered. Okay. If what is that? In the leaky ReLU is concerned with, just to avoid the negative things going to be 0. Okay. Are you with me on this? So there are some networks that is depending upon the data, it is more helpful. Leaky ReLU is helpful in that case, just to avoid the getting the negative activation values to be 0. Okay. So that's only the things, but more or less all are working equally good. Whenever there's such kind of an issue happens with the ReLU, the people go for the leaky ReLU just to avoid the negative activation functions to be 0. That's only. Okay.
Okay, sir. Thank you. Thank you, sir.
All right. So, yeah, but one thing you need to see that, okay, when you moment you go for modification given to this ReLU, no, your computation start increasing. Okay, this is a very simplest form finding the this ReLU things. The leaky ReLU, you're adding a constant that's also still okay, but there is a probabilistic ReLU and all the things that is there. So there again the computation is going to come that increases. Okay, so more or less the ReLU works uniformly well in that things. So especially in the CNN convolutional neural network side, the ReLU is become a de facto. Yeah. Okay. Any more questions?
I think no, sir.
Okay. All right. Okay. It's good. So let's move on to the next these things. I will just stop sharing this and let
Yes, sir.
Sujit
Sujit,
take over that. Okay.
thank you, sir. Huh? Sir.
Okay.
Here-
Welcome.
Yeah.
Yeah.
I think Sujit is here.
So I think
Yes, sir. Yeah, I will share the screen.
Okay.
Right.
Sujit, yeah, Ankisa, just quickly introduce Sujit. Quickly, just 1 or 2 lines, just introduce.
Yes, sir. Good afternoon, everyone. Please allow me to introduce Mr. Sujit Kumar, a dedicated PhD scholar at the esteemed Indian Institute of Technology, Mandi, with a profound background in computer science and a wealth of experience in projects integrating machine learning and deep learning into telecom analytics. His expertise is truly commendable. His current focus lies in the intriguing field of speech processing and recognition, showcasing his passion for innovation and problem solving. His commitment to advancing technology for real-world application is truly inspiring, and his collaborative spirit is sure to make a lasting impact in the realm of academia and beyond. Please join me in welcoming Mr. Sujit Kumar, who will take the session and share his invaluable insight with us.
Welcome, Sujit. Yeah, you can.
Yeah, thank you, sir.
Yeah, just one point I just need to add there. So because I was in IIT Mandi from last 1 decade, so
Yes, sir.
recently
Yes,
only I shifted to IIT Dharwad. So Sujit is a student there, so he will be moving to IIT Dharwad as a continuing his PhD here.
But now currently is in IIT Dharwad. Sujit.
Yeah, I am in IIT Dharwad. He is
No,
in
you are in IIT Dharwad, that we know. Sujit is there in Mandi or Dharwad?
Sujit is in IIT
Currently,
Mandi
I
now,
am
and
at
he will
IIT
be-
Mandi, but soon I will shift to
Yeah,
IIT
right.
Dharwad.
I think
Fine,
in a couple of months he will be shifting.
Okay, okay, sir.
Yeah.
Okay, Sujit. Thank you.
Please go ahead, Sujit.
Okay.
Sujit, go ahead, share your screen.
So I will first quickly go through the performance metrics used in classification, and then I will implement one neural network for the classification with some one example data set. So which sir has explained in this slide, which is uh, the classification of the vowel with the feature as a formant frequency F1 and F2. So first I will go through this uh, performance matrix. So for classification, uh, we need to calculate this confusion matrix, and using this confusion matrix, other performance matrix need to be calculated. So perform this confusion matrix is the table. So it stores the number of sample which is correctly or incorrectly classified. So as you can see in this table, so there is actual positive and actual negative. So this represent the actual level of the data, and there is predicted positive and predicted negative. So this will represent the predicted value, and this matrix stores four values, which is true positive, false negative, false positive, and true negative. So here true positive is the number of samples which is correctly predicted as positive class, and true negative is the number of samples correctly predicted as negative class. So for example, if there is class 1 and class 2, so class 1 will be represented as positive and class 2 represented as negative. And so true positive will represent the actually predicted of class 1, and the true negative represent the correctly prediction of this class 2. And whereas the false negative is the number of sample which is predicted as positive class, but actually it belong to the negative class. And similarly, the false positive is the number of sample of the it belongs to actually is it belong to positive class, but incorrectly predicted as negative. And using this matrix, we can calculate the accuracy. So accuracy is the correctly classification number of sample is it is predicted correctly and divided by total number of samples. So here in the confusion matrix, the diagonal value always represent the correctly classified value. So true positive plus true negative will be the correctly classified samples, and the summation of all the value in the matrix will represent the total number of samples. So we will divide by that. So it will give us the accuracy. And precision is it measures the proportion of correctly predicted positive instance out of all positive all predicted positive. So it is calculated as true positive divided by the true positive plus the false positive samples. And similarly, there is recall. So recall is also known as sensitivity or the true positive rate. So it is calculated as the ratio of true positive divided by the true positive plus the false negative. Similarly, there is another parameter which is F score. So actually it is the harmonic mean of precision and recall. So it is helpful when the classes are like not balanced correctly. Then F1 score is helpful in this one. Then there is other performance metrics like specificity. It is also known as a true negative rate, and it is calculated as the ratio of true negative divided by the true negative plus false positive. Then there is type 1 error, and it is also known as false positive rate, and it is calculated as false positive divided by false positive plus true negative. And the other matrix is type 2 error. So, and it is also known as false negative rate, and false negative rate is calculated as the ratio of false negative divided by false negative plus true positive. And there is another metric which is the ROC curve. It is called receiver operating characteristics. So it is the graphical representation, graphical representation of this classifier performance, and it plots the true positive rate and the false positive rate. And there we can also use the area under this ROC curve. So it is called AUC ROC, and it is calculated as the area under this curve. So these are the 10 important metrics which is used in the classification to check the performance of how the classification is performed. So now after this, I will move to, and there is, as you can see, this is the table. So using this, you can easily remember how to calculate, and easily it can be easily understood by this table. So now I will just give the some Python code how to calculate this matrix using the inbuilt library. So there is inbuilt library scikit-learn. So in this one, we need to import the inbuilt function to calculate the confusion matrix, and there are other inbuilt function available to calculate the performance matrix. So as you can see, we need to import this confusion matrix, and it will take the true levels of the class and the predicted levels, and then it will give us the confusion matrix, and it can be plotted also as the heat map. So I will just in the this neural network demo, I will show how it looks the confusion matrix. Then there is accuracy. So there is accuracy score which calculates the accuracy. There is precision score, recall score, and F1 score. And for ROC curve also, there is inbuilt function available. But for other parameters like true positive rate, then false positive rate, so all those things, we need to write our own code to calculate these performance metrics, because these functions are not available in this library. And as you can see here, in the confusion matrix, I have given it for only 2 classes. So to calculate the confusion matrix for multi-class, so we need to just write the level of the classes, like actual level, and the predicted level, like class 1, class 2, class 3, and then their how many samples they have done the prediction. According to this, if actual class belong to this class 1, and then I will just show one. Okay, I think you will not see the screen. Anyway, so if there is 3 classes, so we can see the actual class and predicted class, and based on that, on particular cell, we will enter the value of how many samples have been predicted to that class. And then if we want to calculate using this formula, so the if for class 1 I want to do the calculation, then class 1 will be considered as the true positive, and the rest of the classes will be considered as the uh, negative class. And then we can add the value of this other 2 classes, so which will give us the uh, total negative sample, and based on that we can calculate these parameters in multi class classification. So if anyone has doubt, then you can ask, because I have not represented the multi-class here. So anyone have any question? Okay, then I will move forward. So now I will give one simple neural network example to uh, classify the this sample data. So first I will show the sample data, how it looks. So let me share the screen. Can you see the new screen?
Yes, sir. It is visible.
Yeah, so this is the 5 classes. So it includes the formant frequency F1 and F2 for this 5 vowels. So let me. Yeah, so as you can see here, so this is the features F1 and F2. Okay.
F1 and F2 are taken from multiple speakers.
Can you repeat?
I'm asking that F1, F2 has taken from multiple speakers, or in a speech where AI continuously said multiple times that are taken.
No, multiple speaker.
Okay, okay.
Yeah, so now, so
Actually, it is
when we perform
from the continuous speech. Actually, it has been wherever that particular vowel is there, that has been segmented. So it has been spoken by the multiple speakers, multiple sessions of the same speaker might be, or it might be occurred in the same sentence multiple times. Okay, that's it. It's taken from the continuous speech. It's not that a person has spoken several times. Okay.
Oh, okay, sir. Got it.
Okay, yeah, that's it. So if that would have been the case, then there would be a very nice data would have been there. But since we have taken this from the continuous conversational speech, actually, so that's why there's some sort of a, when you saw the plot, so there are some sort of a outliers were there. That's because of the co-articulation effect of previous sounds on the extracted vowels. Okay, so that's it.
Okay.
Okay.
So in the classification task, so there are several steps. So first step is for the data set preparation. So if we have the data set, then we need to prepare the data set in such a way that it can be given as an input to the neural network. So like if we have a speech data like audio file, then we need to extract the feature from that, which is already done. So that is F1 and F2 is the features which will be given as the input to the neural network. And in the data preparation, first we need to split the data set into training data set, validation data set, and the test data set. And actually here, as you can see, the training data set has been given 60%, validation and test data has been given to 20%. And it can be changed like according to you can change the split the training, validation and test data set according to your data set. So mostly in training data set, we keep the more data so that it will learn the patterns from the data. So as you can see here, I have imported NumPy and then in SQL from scikit-learn. So there is enable function train test split. So actually it splits one data set into training and testing part. So using this and then there is TensorFlow. From TensorFlow library we have imported two categorical. So actually it will convert our data set labels to the in the format of, if there is 3 classes, then it will convert into like 100 or 001 or 010, like in this format it will convert. So it will helpful in calculating the error calculating error from the like actual level and the predicted level. So here load function will load the files and stored into the NumPy array. Then split data will split the data set into training data set, validation and test data set. And here I am loading the all the 5 vowel data set. Then I'm splitting it all the data set into train class, validation class and test class. And then I'm combining all the data for all the classes. So it can be represented as training data, validation data and test data. I'm combining it all. And I'm also giving the label to each classes. If there is 5 class, so like 0, 1, 2, 3, 4. So these 5 value I have given as the label. And then I have converted to this all the labels into one hot encoding using the 2 categorical function. And then I will just run this. So as you can see, so training data has 7068 samples, and it is 2-dimensional feature vector is, and label size is also 706 set. Then validation data is there and the test data set. So now I will move to, I will just like plot this data set, how it looks. So just it is processing. So I will move to next part, like building the model. So for building the model, we need to import the TensorFlow, Keras, and sequential module also, and the dense model. So this module will help us in building the architecture of the neural network. So as you can see, we have the data set dimension 2. So I have taken the input size 2 and total classes is 5. So I have taken output size 5. And then when we build the model, so as you can see here, so actually dense represent the fully connected layer. So I have given 64 neuron. So there is input dimension and then 64 neuron is there, which is connected to each feature factor. And then there is a hidden layer which is 32, which has 32 neurons. And in both we have used the ReLU activation function. And then the output layer, I have given 3 neurons, with 5 neurons, which is output size. And then I have given the activation function as softmax. So actually softmax will convert the output into a probability. Yeah, so output is already here. So as you can see, this is the scatter plot of the actual data. So there is some overlap, and some of the data set is also completely separable. So like you can see I and A, it is completely separable, and also U and A is also separable, but there is some overlap. Okay, so now the our model is already built. So there is compile function, so which will set the parameter for the model, such as learning rate, which optimization function we will use, which loss function we will use, and if you want some metrics to a store, so it will store the matrix such as accuracy. So as you can see here, I have used the atom optimizer, and learning rate is 0.001, and loss function I have used here is categorical cross entropy. We can use here mean square error also, but here I have used categorical cross entropy. It is like mostly used in multi-class classification. Then for training, we will hello, yeah.
Sorry to interrupt, sir. So there you have used the Adam optimizer. I mean, Sarah has told the gradient descent. So it is
Yeah,
Adam.
that also we can use.
Okay.
So there is a stochastic grade SGD, so that we can also use.
Okay, sir. Okay, sir. Thank you.
It's actually the Adam optimizer is one of the algorithm to implement this gradient descent. Adam optimizer is also a gradient descent method only. I was mentioning, at the end, the gradient descent, the Adam optimizer is a latest advances in the optimization technique in order to make the gradient descent technique move to converge faster.
Yes, sir. Yes, sir. You're
Okay,
totally.
yeah. So because this Adam optimizer is internally, it is a gradient descent method.
Okay.
Okay,
Yes, sir.
so that's the thing. So there are several such optimizers are there. So all of them are the different forms of in the backbone. They are all the gradient descent technique, and in the backbone they are all of the backpropagation learning algorithm. But the additional things they are doing it in order to make them converge faster.
Okay, so now for training the model, there is fit function model.fit, so which will perform the training operation. So in this one, we will give training data and training labels, so as an input, and then how many epochs we are going to run the training, so that we need to give as input. And if we want this to perform the validation, then we need to give the validation data also as an input. Then there is one verbose parameter, so it is only for this like if you want some progress bar to see if it is how it is progress is going on, so for that purpose we can use the verbose parameter. And then this model.fit also, it returns the value. So this the value it is returning is the loss value, and the if we will use the matrix, like as you can see here in compile we have used matrix accuracy, so it will also return the accuracy. So if you want to track the training loss and the accuracy, and we want to perform like we want to plot some graph related to that, then it can be done by using the returning value. So first I will run this model also side by side. So after running this, so as you can see, the progress is showing. So as you can see here, this value that 221. So actually this is the giving the how many batches are there. So actually by default it is taking 32 as a batch size. So there is total 221 batches. So it is for in each epoch, it is for all the batches it is running it. And then as you can see here, it is also giving how much training loss, training accuracy, then validation loss and validation accuracy it is also printing. And I have run this for only 50 epoch. So we can run it for more number of epoch if it is like accuracy, if you want to increase the accuracy, and or we can stop it by at some using some criteria we can put, and then we can stop the training also. And here I have as you can see in this graph, so I have plotted the loss and the accuracy. So here I have used this return value history. So history and then accuracy, and then history validation accuracy. And similarly, you can see here loss and the validation loss. So using that, you can get the loss and the accuracy, and then you can plot it. So after plotting, you can see that loss is getting decreasing, and sometimes it is like increasing and decreasing, but ultimately it is loss is getting decreased. And also in the accuracy, you can see like sometimes it is like accuracy is low and high. It is fluctuating, but ultimately it is accuracy is getting increases. Now, after training has been completed, then we need to perform the evaluation. So evaluation can be performed on the test data set. And there is function model dot evaluate function is there. So model dot evaluate. Using that, we can evaluate the test data. So we can give the input as test data and the test labels, and it will give us the total accuracy and the loss of the test data. So after running this, so I'm getting loss 0.578, and accuracy is around 75.88%. And as you can see in the training, we have got 82, but here it is accuracy is 76% around. And then after like evaluation, we can also perform the like we can get the performance matrix and see how the training, how the model is performing. So we will use the inbuilt functions like confusion matrix. So there is one classification report function is there, which will give us the FS score, accuracy, precision, recall, all those things in a nice table format. Then there is accuracy score, it will give you the accuracy. Then precision score, recall score, F1 score. So all these functions are already available. So we can directly use that, and then we can get the performance matrix. So I will run this code, and I'm also plotting this confusion matrix. So as you can see after running this, so as you can see here, so this is the confusion matrix. And then in the in the visualization format, also you can get the confusion matrix. So how well it is performing. So you can get it, and then it will also it will also print accuracy, precision, recall. And this classification report, as you can see, it will give you in a nice table format. So like for each class, there is total 5 classes, and it will give the precision, recall, F1 score, and support all these metrics in table format. And then we can also plot this ROC curve, and then I have also shown this area under the ROC curve. And then we can there is one function called predict. So there is one evaluate function, and then another is predict. So evaluate function is used to evaluate the like test data, and it will give us accuracy and the loss. But in the predict function, it will give only the probability of the prediction. So it will not give the loss or accuracy. It only just give the prediction of the classes. So as you can see here, so at the end, I have just visualizing how the test data is performing in the plot. So after running this, I will get the yeah. So I have plotted this actual test data and the predicted test data. So as you can see here, there is some misclassification also. So so there is magenta color. So I think I forget to put the legend here. So
Magenta is the U and that color is O.
yeah, so there are some classes which is overlapped. So that one is not like correctly classified. There is some incorrect classification is happening. Also, training is not happened fully. So when we have some overlap uh, data set, then it is difficult to correctly classify. So we need to like run it for more number of epoch, then it might predict correctly. So this much. Then thank you. If you have any question, then you can ask me.
So, if you don't mention the epochs, and then the model will train until the convergence rate becomes 100%. I mean, the error is 0.
No, so if
Or it will grow indefinitely if I don't mention the epoch.
yeah, if there is some convergence will happen, like if error will go till 0, then it will stop. Otherwise, it will run infinitely. That's why we need to put some stopping criteria. So one is the epoch. So at the fixed number of iteration, we need to stop the training. Otherwise, we need to like put some criteria like accuracy. Like if we want 99% accuracy, then just we can write the condition. If accuracy is less than 99 or equal to 99, then just terminate the training. So using that, we can uh, terminate the training process.
So while training, it is validating the accuracy from the validation dataset.
Yeah, so validation is like during training. So it like if one epoch is already done, then based on that, whatever the model has been trained, so on that model it will do the validation. But testing will happen at the end when we have done the model training completely, and then we will test how the model is performing on the test data.
Just to add to the other this thing, so usually the validation data, it's called as a set aside data from the training examples. Okay, so usually in the machine learning domain, this validation data basically is to use to test your model for the different parameter, because there are different parameter you need to tune, right? So this validation data set is used to tune the training data with the different thing to verify that your validation accuracy is good. Okay, then once you optimally choose that, for example, you are having the neural network, so you need to vary the number of layers, number of neurons, right? So each time when you train the model, you test it with using this validation data, and each time you see that, okay, for which architecture your validation accuracy is good. So then you freeze that particular model, and then that will be tested by the test data. So that is the purpose it is used. And in this particular case, actually, that's exactly when it is each epoch, when it is giving the accuracy, it make use of that validation data, which is a part of the training data itself, to verify that how it is behaving with the data which is not seen for that training set. Okay, that's the thing. So hope the doubts are clear.
Yes, sir. Yes, sir.
or
So
added
that's
more
why
dots.
that's why the accuracy while we are testing is higher compared to where we're testing with the testing data set, because testing data is completely unknown to the model.
Exactly. But in this particular case, in the well training thing, what it does is that it uses some from the training set itself, it divides some portion as a learning data set that is used for learning the model. And then you sets aside some 10% or 20% as the validation data to validate it while training the thing. That's what these built-in tools, they follow that thing.
Thank you, sir.
Okay, yeah. Yeah, please go ahead.
Yes, sir. I have a question too, sir.
Yes.
Okay, please can you go back to the training when the model is training? I have a question around the learning rate and the loss function like that.
Yes, yeah.
Okay, I want to see the result. I want to see the output of the training, sir. I have a question around.
Okay.
Hmm.
Yeah, so this is the output. So at the 50 epoch,
Oh, okay, yeah.
so this is
So
the training loss, training accuracy, and then validation loss, and then validation accuracy.
those the outputs of organization like that. Thinking if the learning rates might be reduced, or let's say increase the number of epochs. So my question is just like, okay, if we increase the number of epochs and like reduce the learning rates, will this generalization work, or the model will predict or classify well? So that.
Can you repeat the question?
So my question is, while looking at the visualization or the evaluation of the model, so I discovered that the classif is not well classified in terms of, okay, there are some kinds of data that are out of points like that. So I am just curious if uh, we increase the number of epochs and like reduce the learning rates. So my question is just that if we increase the number of epochs and reduce the learning rates, will it how will it add to the evaluation or the performance of the model?
Yeah, so if we increase the epoch, then the performance may increase. It not always like guarantee that performance will increase. So like it depends on the data set also, like how is the data set. So here if we increase the epoch, then obviously the accuracy will increase, but it is not true in all the cases. It might also decrease. So that's why sometimes we need to put the like a stopping criteria as the accuracy. So when we train the model, and when we see, like as you can see, when we have done this train, so you can see here accuracy graph. So with respect to epoch, so sometime the accuracy is like going like increasing, sometime it is decreasing also. So it is fluctuating as the but ultimately the accuracy is increasing. So we need to like uh, we need to just like run the model multiple times and see where we are getting the highest accuracy, and we need to choose that model. So for our like we need to save that model, and then we can use that model for the testing purpose. So
Okay, so that is well clear. So secondly, I discovered that when working with CNN and other models like LSTM or transformer models like that, I discovered in transformer models, it do take a lot of time. For example, you are training a model or you are fine-tuning a model, it might take more than a week or more than 2 days to do that. So why
yes,
then
yes.
CNN models doesn't take much time as let's say transformer as well for
So
life
it
for life.
depends on how much time it is taking. So it depends on the so actually ultimately what we are doing, we are like training the weights. We are updating the weights in that one, number of parameters. So in the transformer, so there is number of parameter is very huge. So while like doing the calculation, it is taking too much time. So that's why it is taking too much time. Like this, the model I have taken here. So as you can see in this one, how many layers are there? Only this 64,
And also,
32. So weight parameter
just
is, yes, sir.
just so are you using GPU when you are training the model?
Oh no, I was using CPU.
Okay, yeah. So CPU, the transformers models are because the number of parameters to be tuned are very large, and transformers usually they work well when you have the GPU thing because it is a parallel computing. It does very nicely. So that's why if you have a GPU, then it will be fast. So that's the thing.
Oh yeah, okay. Thank you, sir.
Because as Sujit mentioned, no, so it's a very complex model. The number of parameters to be tuned, that is the weight updation. It is a huge number of weights it will be there, and also the data is also will be large, so it will take a longer time when you training in the CPU side. So that's it.
Okay, thank you, sir.
Okay, then. So I think Dileep sir, we can stop here.
I have a question, sir.
Yes. Bala.
Yes, Sujit, have you completed?
Okay, my question is that.
Yes, sir, it is complete.
What is it?
Okay. Fine. Please go ahead. The questions, please go ahead.
Yes, Bala.
Oh, okay. Yeah, my question is that if now we increases the apertures, and is there any means to fast track the best performance of our model within the when we're using high apertures? Is there any means for we that we can be able to track, or we have to go back and check which one is best performance within the apertures?
So you can track it by like you have to write some code in such a way that like you need to like create a log record where you can save your model also in some file, and then you have to save the accuracy, how much accuracy is giving for that model, and based on that like you save it all those things, whatever the for each epoch how much accuracy is coming, and what are the models you are like for each epoch you have to save it, and then at the end you can see which model is, for which epoch which model is performing very well, and then that model you have to choose it. Understood? Or
Yeah, I understood.
yeah.
Okay, then. Okay, I think Sujit.
Yeah.
Yeah.
Yeah. On that is this question, I would like to ask
Yes,
to
sir.
pinpoint some. Yeah. My question is, I learned that it doesn't mean whether the accuracy is high and then the model will be like a very much of precise model like that. So I came across this when I was working on a project, and I discovered that when I wanted to do the performance metrics like that while using confusion matrix, so I discovered in the false negative and false positive are zeros. So there is no false negative, there is no false positive. All are true positive and true negative like that. So in these kinds of models, can I make a conclusion that yeah, my model is precise or not? I'm a little bit
Yeah,
of
so
model.
see, all these metrics are like like which performance metrics would be used. So it depends on the kind of task we are performing. So like as you can see in this one,
Oh, actually, I
yes,
didn't
sir,
get the
yes.
question actually. Can you just, what did you say? So you have false positive and false negative, or everything is false positive, false negative. There is no, sorry, everything is true positive and true negative, and there is no false positive and false negative. Is that the thing you were saying?
Yes, yes, sir.
Okay. And this performance is on test data or validation data or on train data. What is that?
Can you come again? Sorry.
No, it's on the,
Yeah,
no, this,
I can't. I missed your last
no, what
point.
I'm saying is that this performance, what you are getting, is it on the training data or the test or validation?
It's on test data.
Okay, on the test data also, it is giving the, that means that almost like in close to 100% accuracy you are getting, right?
Yes, right.
Okay, so as long as these test data are not used during the training thing, and if you are getting that, then within that context, it is learned well and it is doing good. So that is what we can conclude. Yeah.
Okay.
Yeah.
Thank you, sir. Yeah.
And you don't have any false negative or false positive, right?
Yes, I don't. So when I checked the precision too and all the F1 score like that, all are perfect. I'm seeing the precision
Perfect.
of 100%.
Right.
And
Maybe your
accuracy of
data is quite simpler and your model is not.
oh, okay, sir.
Not many confusions are there. That's what I think. Yeah. Simpler in the sense that's it.
Okay.
Right.
Then Dileep sir, I think we can stop here, na?
Yeah. So if no
Yeah.
more questions, I think we can stop
Yeah.
here.
Okay, attendance
Okay.
I'll take from the previous section. Okay, don't worry for the attendance for this.
Yeah, hope the participants got the good understanding about.
Yes,
At least they
because
got
sir, Dileep sir, most of the students are from Africa, from different countries, also Malaysia,
Right.
France, like that.
Sure.
Definitely, I'll talk with them. If anyone is interested to work with us, definitely we can.
Yes. Sure.
It also will be there, then we can do something.
Right. Okay.
Okay, sir.
Sir,
Then.
sir,
Yes,
should I need to share this Jupyter notebook if they need?
yes. You
Or
can share with me. I will share with them. Dileep sir,
okay,
my
thank you,
mail
sir.
ID is there with Dileep sir. You can.
Yeah. I think he is also having now because I forwarded that thing you
Yes.
just.
You can directly, Sujit, you can share.
Okay, sir, I will do that, sir. Thank you, sir.
Okay, sir. Then thank you very much, sir. Thank you all the participants. Thank you, Dileep sir, Sujit. Thank you very much.
Okay, so thanks all the participants. Thanks for your patience. Okay, so we'll meet again tomorrow evening. I think that's what my next session is.
Yes, sir.
So, yeah. And Murali will be continuing today afternoon and tomorrow.
Yes, at 3 o'clock.
Session that will be continued with respect to the speech. Okay, my
Fundamental.
talk will be on continuation to what Murali has stopped.
Yes. Murli will talk on this, the basics of the speech production.
Exactly. True. So, and then tomorrow on the language identification. So my talk will be where Murli stopped. I will go from there. So,
Yes. Tomorrow, last
the
session will
next,
be yours.
right. So all the sessions are connected things. Okay.
Yes. Murli told me that one. You have planned like that one.
Sure.
Okay, it's good for student. Okay, sir.
Yeah.
Thank you.
Okay
Thank you.
then. Okay.
Yeah.
Thank you.
Bye. Thank you. Good day.
Thank you.